Why do mining operations require weeks to assemble their extraction units at the bottom of excavation pits? A standard highway lane measures 3.7 meters across, a physical constraint that prohibits conventional transport of these structures over public infrastructure. Engineers isolate these mechanisms entirely from the logistical network, forcing a multi-day assembly process directly on the quarry floor. Convoys deliver sections piecemeal, and technicians spend multiple shifts connecting the steel components in geographical isolation. This severe discrepancy in scale creates a permanent barrier between the extraction zone and the outside world. Once the assembly sequence concludes, the operation of these drive units generates a sustained ground vibration. Moving 180 metric tons of extracted material up quarry inclines demands a specific cargo bed geometry, engineered by the Crest Corporation. The physics of coal transport dictate the design. Coal possesses a relatively low density of roughly 800 kilograms per cubic meter. To achieve maximum payload without exceeding structural limits, engineers stretch the dump bed to 13 meters. A standard compact profile would overflow long before reaching maximum weight capacity. The elongated structure distributes the load evenly. At the core of this operation sits a 27-liter diesel engine. It generates 1,200 horsepower. This output translates directly into pure torque. Moving the fully loaded hauler from a dead stop requires immense rotational force. The planetary gear sets lock in to multiply the torque output. The transmission engages. The low hum of the 27-liter engine under load reverberates across the pit. Power flows from the drivetrain into a reinforced hydraulic suspension system. As the hauler tackles steep mine inclines, the heavy-duty automatic transmission maintains forward momentum without losing speed. The suspension cylinders compress under the extreme weight. The hydraulic fluid absorbs the shock of uneven terrain while keeping the machine's center of gravity stable. The scale of the contact patch provides necessary traction. The tires measure 3 meters in diameter. They stand exactly as tall as a standard single-story building. The sheer size of the rubber ensures continuous grip against the loose rock. 180 metric tons advance up the slope. No slipping, no power loss. This exact combination of stretched geometry, massive torque, and specialized suspension changes the extraction logistics. A single Crest hauler executes the continuous hauling cycle, entirely replacing a whole fleet of standard mining transport trucks on the site. A deep, rhythmic mechanical thrum reverberates across the quarry. This acoustic signature belongs to a 46-liter diesel engine converting internal combustion directly into forward thrust. While wheeled vehicles handle transportation logistics, initiating the primary displacement of solid rock requires a rigid crawler platform weighing 152 metric tons. The Komatsu Superdozer applies 1,150 horsepower strictly to generate pushing force. The transmission transfers this torque to heavy steel tracks that clank against the hard rock, locking the chassis into the terrain. Static mass serves as the critical factor here. The weight presses the rigid suspension firmly into the ground to prevent track slippage under maximum load. With traction secured, the machinery drives a steel blade measuring 7 meters across into the geological face. A single pass displaces 69 cubic meters of material. That volume equals the exact capacity of 2 standard 20-foot maritime shipping containers. Managing this immense earth displacement involves strict spatial constraints. Ground spotters relay positioning signals via radio, directing the operator maneuvering the 7-meter blade within narrow excavation corridors. The hydraulic cylinders extend, shifting the earth forward while the engine maintains a steady hum under the structural strain. Ground teams spend 2 full days just to safely unload a single unit from the transport trailer. Crawler platforms hit their structural limit near 150 metric tons. Modern copper pits demand moving 400 metric tons in a single run. The Caterpillar 797F answers this logistical deficit. A 2-axle chassis carries an extreme payload. 4 main tires, each standing 4 meters tall, bear the entire weight. They support a gross mass of 687 metric tons. The contrast is sharp. A narrow 2-axle footprint must stabilize hundreds of tons of loose rock on uneven ground. To move this mass, the vehicle utilizes a 20-cylinder diesel engine. Displacement reaches 106 liters. This internal capacity matches the combined engine volume of 50 standard passenger cars. The block generates 4,000 horsepower, transferring torque through a 7-speed transmission. Operating on a steep mine descent pushes the structural integrity to the limit. Gravity pulls the loaded chassis downward. Electronic sensors intervene. The management software continuously calculates load distribution, dynamically adjusting the braking force across the massive wheels. Hydraulic fluid surges, heavy calipers clamp down. The friction generates intense thermal loads. The sharp smell of roasting metal from the brake pads cuts through the quarry dust. The machine balances constantly on the physical edge of two-axle capability. 4,000 horsepower fights gravity on every incline. This extreme specialization creates a hard geographic boundary. A gross mass of 687 metric tons permanently locks the vehicle inside the excavation zone. It physically cannot leave the pit to touch standard asphalt. A Belarusian heavy haul truck pushes the payload ceiling outward. The fully loaded mass exceeds 800 metric tons. Achieving this capacity creates an immediate logistical crisis. The industry now requires entirely new loading equipment just to fill a single truck bed. The mechanical solution relies on a diesel-electric transmission architecture. Two V20 diesel engines sit inside the structural chassis. Together, they generate 4,600 horsepower. The deep, low-frequency roar of the twin diesel blocks fills the excavation pit. However, these engines do not connect to traditional mechanical drive shafts. The diesels are exclusively high-output generators, feeding electrical current directly to 4 independent wheel motors. An 8x8 all-wheel drive system distributes the traction forces into the crushed rock surface. Maintaining structural integrity under an 800-ton load demands specialized physical dampening. A hydropneumatic independent suspension system supports the steel frame. Nitrogen gas and hydraulic fluid compress within the internal cylinders, absorbing the cyclic impacts of the mining terrain. The scale of operation requires substantial onboard fluid reserves. The primary fuel tank holds 5,000 liters of diesel fuel to maintain continuous shift cycles. Engineers deliberately minimized non-essential space, compressing the operator cabin dimensions and keeping the exterior access ladders strictly functional. In 2014, this specific 450 metric ton payload capacity officially secured a Guinness World Record. To fill a 450 metric ton dump bed, the extraction industry deploys hydrostatic excavators weighing 811 metric tons. The Hitachi EX8006 answers this exact logistical crisis. Its physical footprint easily exceeds the total surface area of a professional basketball court, stretching 15 meters long and standing 10 meters tall. Power generation starts at the rear. Twin Cummins V16 engines run simultaneously. Together, these blocks deliver a combined output of 3,880 horsepower. This mechanical energy does not turn conventional drive shafts. Instead, the engines pressurize a highly complex hydrostatic transmission system. Hundreds of liters of hydraulic fluid move through heavy-duty reinforced hoses. Independent closed-loop circuits route this extreme fluid pressure directly into the massive boom cylinders and track drive motors. Cycle speed strictly dictates mining profitability. The internal fluid architecture operates under continuous maximum compression. It maintains rapid boom velocity, translating engine torque into immediate lifting force. 75 metric tons per swing. This represents 45 cubic meters of blasted rock, hoisted clear off the ground in one single motion. To grasp this scale, the steel bucket spans a width wide enough to park 2 full-sized passenger automobiles side by side. Through this precisely calibrated hydrostatic setup, the excavator maintains an aggressive loading pace. A standard 300 metric ton haul truck is completely filled in just 4 to 5 consecutive passes. The entire cycle compresses loading time from extended hours down to a few intense minutes. Meanwhile, the operator cabin remains strictly functional. Engineers stripped away unnecessary interior bulk, focusing the design entirely on external cycle volume. You will find these massive digging machines across major high-output open pits in Australia, Canada, and Chile. They constantly excavate coal, copper, and raw gold ore. Constant digging exposes every metallic joint to severe environmental friction. In one specific operational case, engineering teams modified the entire hydraulic circuit with specialized corrosion-resistant components to survive the harsh chemical conditions of a remote lithium mine. Hydraulic fluid dynamics hit a strict pressure limit during continuous heavy operation. To lift 90 metric tons in a single cycle, engineers abandon standard diesel engines entirely and shift toward high-voltage electrical networks. The resulting machine utilizes raw grid power instead of internal combustion. This specific configuration creates a heavy-duty electric rope shovel weighing 1,270 metric tons. Thick electrical cables feed continuous electricity directly from the local power grid into the primary machine infrastructure. A massive electric motor drives the mechanical functions, emitting a steady, low-frequency hum rather than the loud, rhythmic exhaust noise typical of traditional heavy diesel equipment. Instead of pressurized hydraulic fluid pushing rigid steel cylinders, this electrical rope shovel relies on purely mechanical tension. Thick steel cables wind around rotating drums to pull the front bucket upward. Steel winches engage under maximum load. The 30-meter structural boom extends forward to position the bucket directly against the rock wall. Heavy steel ropes pull 90 metric tons of excavated material in one continuous upward motion. The internal payload capacity reaches 120 cubic meters per pass, requiring immense kinetic force generated directly by the main electrical drive. A distinct operational contrast defines this specific excavation mechanism. It relies on a stationary, high-voltage power connection, dragging thick, trailing cables across the dirt, yet it remains fully mobile across the fractured mine floor. The entire structure travels on gigantic crawler tracks. Each individual track is wide enough to parallel the physical dimensions of a standard freight locomotive, distributing the massive weight evenly over the uneven ground. This electrical configuration dramatically reduces internal friction and extends the operational lifespan of the core lifting mechanisms. One specific machine operating in a Wyoming coal mine has been continuously working for more than 20 years with only minimal technical updates. 90 metric tons was never the ceiling for this cable-driven architecture. Engineers escalated the electric motor output to nearly 10,000 horsepower. The P&H model represents a critical threshold in single bucket extraction. A new engineering problem emerges. How does a steel frame endure 1,400 metric tons of mass during constant rotation? The solution relies on an integrated rotating platform working in tandem with heavy-duty shock absorbers. During extreme cyclic loading, every dig sends high-velocity kinetic feedback through the lower chassis. To prevent microscopic fractures from tearing the steel apart, the suspension systems continuously dissipate the structural shock. The frame holds steady, the cycle repeats. The true scale of this operation becomes visible at the bucket. The dipper grabs 122 metric tons of rock in a single movement. This payload roughly equals the mass of 2 fully armed main battle tanks lifted simultaneously. The cables pull the load upward. The entire upper deck rotates to drop the material into waiting haul trucks. This establishes the physical limit of point-to-point excavation. Going larger requires continuous rotary systems. The operational history of these units proves their mechanical endurance. They run constantly. High-voltage cables feed grid power directly into the motors. Maintenance windows remain critically short. These electric shovels operate up to 22 hours a day in North American copper mines. One specific unit received a custom red, white, and blue exterior. Crews named it Liberty. The components endure heavy friction and thermal wear. After 22 hours of continuous payload loading, the heavy gears finally grind to a halt. The necessity of driving a multi-lane highway through dense geological strata directly beneath Seattle demanded the assembly of a 7,000 metric ton boring complex. Named Bertha, this tunnel boring machine was not merely an excavator. It was a fully automated subterranean assembly plant. The rotating cutter head measured 17.5 meters in diameter. Its mass equaled the combined weight of 70 mainline electric locomotives. Behind the massive front shield, 25 electric motors generated 8,000 horsepower to drive the main rotation gear. The earth fractured. Hardened steel discs sliced through the dense clay and glacial till. Simultaneously, a dull scraping of thick metal resonates 60 meters below the active city foundations. As the rock shatters under heavy pressure, internal conveyor belts immediately capture the loose debris. The material travels backward through the 100-meter-long internal structure to the surface. The critical engineering challenge involved preventing the urban infrastructure above from collapsing into the newly formed void. A complex system of hydraulic thrust cylinders pushed the massive machine forward, advancing millimeter by millimeter into the solid ground. While the front face ground through soil, the internal assembly shop operated continuously directly behind the protective shield. The mechanism instantly delivered heavy reinforced concrete segments to the newly exposed tunnel walls. Heavy hydraulic arms positioned these curved sections into place. They locked them together to form a permanent structural ring before the surrounding earth could settle. The process was continuous. This simultaneous excavation and installation created the permanent structural shell of the 3.2-kilometer highway tunnel directly during the forward advance. The slow, calculated progression protected overhead office buildings, underground water mains, and surface highways from subsidence. Engineers monitored the ground settlement continuously from the internal control rooms, adjusting the hydraulic forward pressure and concrete grout injection to maintain structural equilibrium. Despite encountering severe mechanical delays midway through the project, the machine successfully breached the final concrete retaining wall in 2017. The massive cutter head was subsequently dismantled into smaller steel sections. Today, several fragments of the heavy cutting discs stand as public art installations across Seattle parks. If Seattle demanded millimeter precision, the Ohio coal fields of 1969 required the extraction of 170 cubic meters per cycle. The Bucyrus Erie dragline excavator was engineered to strip away thick layers of barren rock. The physical dimensions immediately revealed the sheer scale of the operation. The steel boom extended 95 meters into the air above the pit. The total mass of the machine reached 13,000 metric tons. Kinematics of such a heavy structure relied heavily on uninterrupted energy flow. External trailing cables feed high voltage directly into the primary electrical distribution panel. The electric load surges. Thick cables pull taut. The massive bucket slams into the soil. It shears away bedrock in one continuous motion. High voltage power lines vibrate visibly under the intense peak electrical load. A complex array of internal electric motors generates 18,000 horsepower. This power drives the swinging and hoisting mechanisms. The bucket engulfs nearly 300 metric tons of earth in a single scoop. The boom supports this immense payload while swinging over the spoil pile. Mobility remained a severe physical constraint for the operators. Conventional track systems could not support 13,000 metric tons of concentrated mass. The base would sink. Instead, the excavator utilized an elaborate walking mechanism. 4 giant hydraulic shoes deployed on the sides of the main hull. These steel pads pressed firmly into the ground. Massive hydraulic cylinders lifted the entire chassis several meters into the air. The frame dragged backward. It rested back onto its circular base after each lifting cycle. Relocating this colossal structure to a new digging position required several days. The extreme weight dictated a painfully slow kinetic cycle, yet the daily output remained exceptionally high. Over its active operational lifespan, the dragline displaced 600 million tons of geological material. This excavated volume equals 2.5 times the total earth moved during the construction of the Panama Canal. When coal extraction operations ceased, the main housing and walking mechanisms were completely scrapped. Today, the steel bucket stands alone, preserved as a permanent public monument in Ohio. From single bucket throws, engineers shifted toward the continuous rotation of a structure weighing 14,200 metric tons. Constructed in 1995, this bucket wheel excavator stretches 96 meters into the air. That vertical profile directly matches a 30-story commercial building. How do you move an object weighing over 14,000 tons across the soft dirt of a mine floor? The solution requires a distributed network of crawler tracks. These wide tread assemblies displace the massive weight across a huge surface area. This prevents the steel structure from sinking into the ground of the Hambach open pit mine, a site reaching depths of nearly 500 meters. The operational contrast dictates the entire process. The base assembly creeps across the bottom of the excavation zone at a fraction of a kilometer per hour. Meanwhile, the internal mechanics move at a completely different pace. At the front end, a rotating wheel equipped with 18 steel buckets performs the extraction. Each bucket scoops exactly 6.6 cubic meters of lignite brown coal in a single upward pass. The wheel spins steadily against the rock face, shearing off material. As each bucket reaches its highest point, the raw coal drops downward onto a high-speed internal conveyor belt system. A continuous, monotonous hum of 16,000 horsepower echoes through the extraction zone. Electrical power flows through external high-voltage cables directly into the drive motors. The fast-moving internal belts transport the crushed lignite across the 225-meter length of the machine. Operators monitor the flow from an elevated cockpit featuring digital command systems. The fuel travels directly to nearby power plants, maintaining the base energy supply for the surrounding regions. There is no pause for repositioning a dragline. The operation yields 240,000 cubic meters of material every single day. The daily extraction of hundreds of thousands of cubic meters of coal across Germany, or continuous tunneling through the United States, leaves physical alterations deep within continental structures. These heavy mechanisms remain hidden from urban centers. They process material in remote surface mines or carve out deep subterranean transit routes. Yet their output directly supplies regional power grids and reshapes the geological profile of the crust. The Hambach surface excavation site in Germany now reaches a depth of 411 meters below sea level. This geographical depression is a direct result of continuous rotary extraction. Decades of operation displace billions of metric tons of sedimentary bedrock and topsoil. The original stratigraphy is erased. The missing mass alters local groundwater flow. When the steel structures are finally decommissioned, their operational footprint remains. The rock strata do not recover. Voids cut beneath the streets of Seattle and the terraced craters of European coal quarries remain fixed into the surrounding landscape.